Oh, Carolyn Walking is here. Online. Okay, so let me turn on the projector. Oh, Carolyn Walking is here. Ooh, online. Okay, what did I do wrong here? Oh, I know what. Let me see. Let me see. Testing. Okay, no, I'm good. Okay, so assignment number 2. So let me bring it up on the screen. Okay, seems as if I've closed the poll. Wait a minute. All right, here we go. Here we go. Assignment number 2. Okay, so if I'm not mistaken, and please, I think we got as far as question number 3, and I told you guys to try the others. So, any questions about any of these? Or do I need to just continue with the rest of the assignment? Or let me get my writing here. Have you tried any of the rest of the assignments? Or do you need help in any of them? How about you guys out there in Zoom? Any questions? For number 4, number 5, number 6, number 7, number 8, number 9, 10, 11. Well, we did 12 already, right? 12 was a rate law question. 12 and 13, I think.
Yeah.
Right, so just a matter of the others that we have not done. So, okay, somebody has a question. Let's see. Okay, so somebody's asking for us to work through number 5. So let's see what number 5 says. Number 5 says the rate constant for the first order decomposition of, and it gives you the equation, is 6.32 times 10 to the minus 4 seconds to the minus 1. So the question is, what is the concentration of N2O5 remaining after 2 hours if the initial concentration of N2O5 is 0.500 m? So for this question, the equation that comes to mind is, oops, it's full screen. Okay, so the question that comes to mind is the equation relating the rate constant, relating the concentration of a reactant to time for first order reaction. And that equation is, well, there are a couple of forms of that equation. One form is A, concentration is equal to the concentration initially of A times E to the minus KT, right? There are other forms, just to remind you. We have this form here. Oops. Right? These are 2 ways of saying the same thing, right? And which of these you use is dependent on what you're given in the question and what you're expected to get. So in the case of question A, it says, what is the concentration of N2O5 remaining after 2 hours if the initial concentration of N2O5 is 0.500 m? So in this case, this would be the initial concentration, right? They gave you the time and they gave you the rate constant, which is this right here. So basically, I'll be using this form of the equation to answer this question, right? So basically, the concentration of N2O5, based on this equation, will be equal to the initial concentration, which is 0.500 m, times e to the minus k. So k is given as 6.32 times 10 to the minus 4 seconds to the minus 1, multiplied by the time, which is 2.00 hours. However, we need to keep the units compatible with each other. We have seconds to the minus 1 here. We have hours here. So what I would do is convert the hours unit to seconds. And of course, you should know that 1 hour is equal to 3,600 seconds. All right? So in terms of what units will cancel out, the hours will cancel out here and here. The seconds will cancel out here and here. And then we have to do the math, which I think I've done already. Let me see if I can locate it here. So number 5, okay. So according to my calculation, and again, please check to see I'm doing the right thing, but according to my calculation, I got 5.28 times 10 to the minus 3 m. All right? And that's how that is done. All right? Any questions about that one? Any questions? Any questions? Nope. Any questions out there in Zoom? Something is wrong here. Okay. All right. So let's look at the B part. In fact, let me clear this first. It's okay for me to clear this, right? Okay, let me clear this. And then let me do this and scroll down. Okay, now the B part says, how long will it take, in other words, the time required, for 90% of the N2O5 to decompose, all right? So let me turn on my thing in. Okay, so in this case, remember now I gave you 2 alternative equations to use. In this case, I would use this equation, Ln concentration of A over the initial concentration of A is equal to is equal to minus KT, all right? So that would be the form of the equation I would use. And the reason why I do that, or use this form, is because I can easily rearrange it to get an expression for T. So T would be equal to minus 1 over K times Ln concentration of A over concentration of A initial, right? And it's all a matter of putting the numbers in. Now, here's where you have to be careful. You have to interpret this part of the question carefully. It says, how long will it take for 90% of the N2O5 to decompose? So what does that mean? That means that at that time, right, whatever the time is, there'll be 10% of A remaining, or 10% of the initial amount of A remaining, right? So therefore, what this means is that this ratio here would be 10%, right? So therefore, all we have to do now is plug in the values for K, which is, what was it already, from before? It was 6.32 times 10 to the minus 4 seconds to the minus 1, Ln 0.1. And according to my calculations, when I did it, I got 3.64 times 10 to the 3 seconds. And that's how we do that. All right? Any questions about this one? Any questions out there in Zoom? Any questions? Okay. In the case of the C part, it says how long will it take for 90% to remain, right? So in this case, what they're saying is that 90% of the original A concentration will be remaining, and you have to calculate the time at that point. And it's very simple. It's similar to what we just did. The only difference is that we're going to replace the 0.1 with 0.9, right? So in this case here, T will be equal to minus 1 over 6.32 times 10 to the minus 4 seconds to the minus 1, Ln 0.9. And according to my calculations, this works out to be equal to 1 167 seconds. And that's how that is done. All right, any questions about that one? Questions? Okay, is it okay for me to clear this? Okay, so the next question is how long will it take for 50% to remain? So what formula would come to mind when it comes to this question?
Same one we just used.
Well, you could do that, but there's a simpler formula for first order reaction. What?
Half-life.
Exactly. I was about to ask you, what is the time taken for half the amount to react? That's called the half-life. And in the case of first order reaction, the half-life is given by this equation, ln2 over k. All right? So ln2 divided by k, and k was 6.32 times 10 to the minus 4 seconds to the minus 1. And when I did that calculation, I got 1.10 times 10 to the 3 seconds. And that's how that is done. All right. Any questions about this one? Any questions? Questions? All right. Any questions about any other of the problems in this assignment that you need help with?
Could you go over number 7?
Number 7. Okay, so I can clear this, right? Okay, so scroll down to number 7. Okay, so number 7. Okay, so this one deals with activation energy and how it relates to the rate constant. So just to briefly describe what's happening here, this is something that was covered in the videos that I've posted. So I'm just going to give you a brief synopsis of what is involved here. So basically, what we're looking at here is the effect of temperature on the rate of reaction. And it turns out that there's a relationship, an equation, the Arrhenius equation, which is just going to write it up here. K, the rate constant, is equal to A times e to the minus EA over RT, right? So just to identify the different terms, K is the rate constant for the reaction. A is what is called the frequency or collision factor. What do you call it again? I think it's called a frequency factor, right? Or collision factor. I'll have to look it up. EA is the activation energy, right? R is called the molar gas constant. And T is the temperature in Kelvin, right? Now, here's the thing. The activation energy, I would say, is probably the most important term in this equation. It represents the energy required for the reaction to take place. Now, to describe what happens at a microscopic level, basically what happens is that when a reaction is taking place, you have the collisions of molecules, the reacting molecules colliding with each other. According to the collision theory, however, not all collisions will result in a reaction. It all depends on how much energy the reacting molecules have. If the reacting molecules have below the threshold energy, which is the activation energy, then basically what will happen is that the molecules will collide and bounce off each other without undergoing any change, right? But if the molecules have that minimum activation energy, then you'll have a successful reaction. You're going to have bond breaking, and then eventually bond formations for the new products, right? So the activation energy is considered to be like the energy barrier, right? The more molecules that you have, or I should say, the more molecules that will have at least the activation energy will allow the reaction to take place, right? And therefore, the faster the reaction rate. Now, there are things that can be done to increase the reaction rate. Two things actually would be the main two things that you can modify the reaction in order to increase the reaction rate. One is to increase the temperature. Well, actually, yes, one is to increase the temperature, right? And one can see that in this formula right here. Because if you look at the algebra of this formula right here, you'll see that as the temperature increases, the K value increases as well, all right? So that's one thing. Another thing you can do is lower the activation energy. So you might be wondering, how do we do that? And basically we do that by adding a substance, which is called a catalyst, all right? A catalyst basically, simply put, it's a bit more complex than this, but simply put, when you add a catalyst to a reaction, basically the catalyst will change the reaction mechanism and the pathway will have a lower activation energy. And as a result, if the activation energy is lowered, then the reaction rate is increased, right? So those are just two simple ways of increasing the reaction rate. So if you increase the temperature or you lower the activation energy by adding a catalyst, then either one or both will increase the value of K, which is a rate constant. And if you increase the rate constant, then the rate of the reaction increases. All right, that's basically an overview of what this equation is all about. So getting back to this question, the question says calculate the activation energy for the decomposition reaction. So basically what the question is asking is for you to calculate the activation energy. So they gave the rate constant at 300 degrees be equal to 5.7 times 10 to the minus 1, m to the minus 1, s to the minus 1. And at 230 degrees Celsius, the activation energy changes to 2.7 times 10 to the minus 2, m to the minus 1, s to the minus 1. All right, so basically you're given a particular temperature. I'm going to call this T1, and we have to convert this to Kelvin. So we have to add 273 to this. So if you add 273 to 300, that gives you 573 Kelvin, right? So I'm going to call this temperature T1. I'm going to call the corresponding rate constant for that K1. And then for T2, again, you have to add 273 to this. So if you add 273 to 230, you're going to get 513 Kelvin. So this is T2. And this is, I'm sorry?
503, not 513.
503, my bad. Yeah, you're right. 503 Kelvin, thank you. And the corresponding rate constant would be K2, right? Now, as I said before, K would be equal to A, e to the minus EA over RT, right? That's the equation I just gave you here. So what I'm going to do here is specify this equation here for the first set of conditions. I'm going to put K1 here and T1 here, and then write a similar equation for K2, A, e to the minus EA over R T2, right? So this is for the first set of conditions that I have here. This K2 expression is for the second set of conditions right here. What I'm going to do is divide one by the other. The A's will cancel out. So you're going to end up with K1 divided by K2 equal to E to the minus EA over R. I'm sorry, EA over R times 1 over T1 minus 1 over T2. So this is just another way of expressing the relationship between the rate constant and temperature. But in this case here, you have two sets of values for the rate constants and the corresponding two sets of values for the temperatures, right? So this question is asking for us to solve for EA, right? We have everything we need to solve it because we have the K1 and K2 values. We have the T1 and T2 values, and R, in this case, we're going to use the value for R being equal to 8.31 joules per mole Kelvin, all right? So it's a matter of rearranging this. So how do we rearrange it? Some algebra will be involved. The first thing I would do, and this is something that you should be familiar with from your previous math courses, the first thing I would do is find a natural log of both sides, right? So ln K1 over K2 for the left side would be equal to minus EA over R 1 over T1 minus 1 over T2. And then finally, what I would do is solve for EA, and that would be equal to R ln K1 over K2 divided by 1 over T1 minus 1 over T2. And then what I would do is put the numbers in. So don't forget the minus sign, very important, all right? So minus 8.31 joules per mole Kelvin, we'll go up top here, times ln K1, what's K1? K1 is 5.7 times 10 to the minus 1, m to the minus 1, s to the minus 1, all divided by K2, what's K2? 2.7 times 10 to the minus 2, m to the minus 1, s to the minus 1. And then I will divide that by 1 over T1. What's T1? T1 is 573 Kelvin minus 1 over T2, which is 503 Kelvin, right? And when I did that calculation, and again, please check to make sure I'm doing the right thing. But when I did that calculation, I got 1.04 times, oh, by the way, Kelvin units will cancel out here and here. So it's 1.04 times 10 to the 5 joules per mole Kelvin. And that's how you do that one. All right. Any questions about this one? Any questions? Questions?
I do have one question.
Yes,
You
sir.
said that with an increase in temperature, there'd be an increase in K. How does that work with that formula? Because it looks like if you increase K, increase T, K will decrease.
Well, let's see here. The temperature here is 300 degrees Celsius and K is this, right? So when the temperature is decreased to 230, K is this, so it's a decrease.
Okay,
2.7 times 10
Yeah.
to the minus 2 is less than.
that makes sense. Okay.
Exactly. Okay, any other questions? Any other questions? Yes, ma'am. Number 10. Is it okay for me to clear this?
Yes.
Okay, all right. So scrolling down, number 10, let's see what 10 has to offer. Okay, now 10 deals with reaction mechanisms, right? So briefly, when we're talking about a mechanism of reaction, we're talking about a detailed step-by-step description of what is happening as the reactants are converted to products, right? So more detail is involved compared to just given an equation. An equation doesn't tell you the step-by-step process. And let me just say here, and I just noticed it here, here's a typo, a slight typo, but it's important. Let me show you what the typo is. The typo is that there should be a K right here. So please make a note of that. There should be a rate constant right there. I apologize for that, all right? Okay, so the question says, it gives you the equation, and then it says, show that the following proposed mechanism is constant with the experimental rate law, and the rate law is rate is equal to K times concentration of H2 times concentration of NO2 squared, all right? Okay, so, one thing I should mention before I move on to this, right? And again, this should be covered in the videos I posted, but let me just mention this quickly. So, as I said before, the mechanism will be a step-by-step description. Most mechanisms will have more than one step. There are a few exceptions where there's only one step, right? Now, if you have more than one step involved in a mechanism, then they're not going to be proceeding all at the same speed. There are different factors that would affect that, right? And for those of you who have to do organic chemistry, you're going to learn more about that. But simply put, I'm just going to say here, and you can just accept this as fact, that not all steps will proceed at the same speed, right? Some will be slower, some will be faster, right? The step that is the slowest, we call that the rate determining step. In some textbooks, they call it the rate limiting step, all right? And the reason why it's called as such is that that step determines the overall rate of the reaction. The rate of the reaction overall cannot proceed faster than the rate determining step, all right? So pretty much anything, and again, this is something for those of you who have to do organic, you're gonna learn when it comes to organic reactions. any factor that affects that step affects the rate of reaction, right? And there are several factors that can affect that step. Temperature is one of them, you know, the structure and the three-dimensional orientation of molecules can affect it and all that. So that's one important fact that will come into play in this question, because the first thing you would do in order to answer this question is to write down the rate law for the rate determining step. So this here is a rate determining step that's indicated right here, right? Now, when it comes to writing down the rate law for any step, it's very simple. All you have to do is go by the stoichiometry of the equation, especially when it comes to the reactants. So for step number 2, the rate determining step, the rate law is rate is equal to K2 times the concentration of N2O2 times the concentration of H2, all right? So that's the first thing I would write down, right? The rate of the rate determining step is equal to K2 times the concentration of N2O2, times the concentration of H2, all right? Now, here's the thing. The rate law only contains terms for the concentration of the reactants in the overall reaction, right? So what we have here is one reactant coming from the overall reaction here. But in this rate determining step, we have another reactant. That other reactant is not present in this equation here. So we need to express this reactant in terms of the original reactants involved in the equation. So how do we get that expression? We turn to this equation right here, right? Now this equation, they say it's a fast reaction, and you'll notice that it's a reversible reaction, right? It goes in both directions, right? The assumption is going to be that this will be at equilibrium. And we're going to talk about equilibrium in more detail in the next chapter. So let me just write here. The assumption that in step 1, the reaction is in equilibrium, right? So what does that mean? When we talk about equilibrium, equilibrium basically means that the rate of the forward reaction will be equal to the rate of the reverse reaction, right? That's what equilibrium means. So basically, if we're going to assume that to be the case, then we can say that for the forward reaction, for which the rate law is K1 times the concentration of NO, O squared, that will be equal to K minus 1, which is this right here, times the concentration of N2O2, all right? So that is the equation based on the assumption that that particular first reaction is proceeding in both directions at the same rate. In other words, in a state of dynamic equilibrium. Now we can do this. This N2O2 here, which is this right here, we can express it in terms of the concentration of NO2 based on this equation. So we can say that the concentration of N2O2 is equal to K1 times the concentration of NO squared divided by the concentration of N2O2, right? And therefore, now that we have an expression for N2O2 in terms of one of the reactants originally in this equation right here, we can plug in this expression here into the rate equation for the rate determining step. And when we do that, we're going to end up with rate is equal to K2 times K1 times the concentration. Oh, so hold on, I made a mistake. What's the mistake I made? This should not be here. Okay. Okay, so K2 times K1 times the concentration of NO squared. I'm missing something. K minus 1. All right, tell you what, let me make this more neater. Let me erase this here. Sorry about that, folks. We should have K minus 1 down here. All right. So plugging all of this where this is, you're going to get K2 times K1 over K minus 1 times NO squared times H2, right? And if you look at this equation carefully, you'll see that this equation is pretty much the same as this equation. So basically, all I'm gonna say is that this is equal to K concentration of NO squared concentration of NO squared times concentration of H2, where K is equal to K2, K1 over K minus 1. And that's it, right? Basically, what we have just done is using the mechanism is to prove that the rate law, it supports the rate law that has been experimentally determined for the reaction. All right? Okay, any questions about this? Any questions? Any questions out there in Zoom? Or any other questions about any of the other problems?
Number 9.
Number 9. Okay, let's clear this. Scroll up. Okay, number 9 is again related to mechanisms. It says, given the following mechanisms for reaction, and it gives you the steps involved, identify the intermediate and catalyst, if any. Okay, so here we have to go back to what was covered in the videos, right? Because in the videos, I made a distinction between intermediates and catalysts in a mechanism. An intermediate in a mechanism is a species that is produced in one step and then used up in a subsequent step. All right? An intermediate is a species that is used up in, I think I have it backwards actually. Let me rephrase that, just in case I made a mistake first time. An intermediate is a substance that is produced in one step and used up in a subsequent step. That's what I said, right? I think, yeah, okay, good. So that's an intermediate, right? The catalyst, on the other hand, is a species that is used up in one step and then produced in a subsequent step. So they're kind of opposite, right? So just to recap, just to make sure we're all on the same page, an intermediate is a substance that is produced in one step and then used up in a subsequent step, while a catalyst is one that is used up in an earlier step and then produced in a subsequent step, all right? So based on those definitions, right? In terms of intermediate, write this down here. Oh, turn on this here. Okay, so in terms of intermediate, I would say that the chlorine atoms produced here is an intermediate because it's produced in the first step and then used up in the second step, right? So the intermediate here would be the chlorine, not the Cl2, but the Cl, all right? So the catalyst, as I said before, is used up in an earlier step and produced in a subsequent step. So based on that definition, what would you say the catalyst is? Based on the mechanism provided. Catalyst is used up in an earlier step and produced in a subsequent step.
Cl2.
Cl2, exactly. So the Cl2, whoops, would be the catalyst, all right? And I just realized something. Let me just see here. There's also another intermediate. So you can have more than one intermediate. Can somebody tell me what that intermediate is?
CLO.
The CLO, exactly. CLO is produced here and used up here, right? So there are two intermediates here. One is Cl and one is ClO, all right? Okay. Any questions about that? Any questions about that? Yes, ma'am.
Just to reiterate, the intermediates are like consecutive steps.
Not necessarily consecutive, but subsequent. So, you know, you could have an intermediate produced in the first step, and then you could have 2, 3, 4 steps, and then the intermediate is used up. Sometimes that happens, right? As long as it's one before the other, but there could be some intervening steps. In this particular case, it's, you know, consecutive, but not necessarily. It's just that it's just as after.
How did you determine the catalyst?
The catalyst is one that is used up in one earlier step
Okay.
and produced in a subsequent step. And again, you can have intervening steps, so
Okay.
they don't have to be immediately or consecutive, as long as it's subsequent, all right? Okay, so that's A. The B part says, what is the molecularity of step number 3? Now, molecularity is a very simple concept. It basically means how many molecules are involved in a particular step as a reactant, right? So the answer for B would be what? How many molecules are involved in step number 3 as reactants, not as products, as reactants? 2, exactly. So the answer here would be 2, because you have 2 molecules of the ClO involved, all right? And then it says, which step determines the reaction rate, and write the rate law for that step, all right? So we just talked about in the previous question we looked at. We talked about the rate determining step, right? So based on the information provided, which step would be the rate determining step? Step 1, right? So the answer is step 1. And the question is asking for the rate law for that step. Let me scroll down here. Okay, you know what? Let me just get rid of all this here. Okay, so for step 1, okay, so for step 1, okay, so as I said before, the first part of the answer is step 1. And what would be the rate law for that step? Step 1. Rate is equal to what?
K times the concentration of Cl2.
Exactly. And that's it. Now, typically, if you had given me this in a test, I might be correct. But typically, what would happen in some question is that they would say that this is K1, this would be K2, or this would be K3, right? So in that case, you put K1 right there, all right? Okay, is there any following questions after this?
Yeah, there's a part D.
Okay. Okay, write the overall reaction equation. Now, okay, now remember I had a problem with this question because I don't think it's possible for you to write a rate law for the overall reaction. Well, yes, you can actually. What am I thinking? Okay, so, wait, somebody has a question. Or somebody's asking for me to work through number 4. Okay, I'm gonna do number 4 as soon as I'm finished with this. All right, so it says write the overall reaction equation and the rate law for the overall reaction, right? Let me clear this. Let me, okay, so let me keep this here because one thing you need to remember is that whenever you're writing down, whenever you have a mechanism for the reaction, when you add up all the equations for the mechanism, it should add up to the overall equation for the reaction. So basically what you need to do is add them up, add all of these equations. Now, you should know from your previous chemistry experience, when you're adding 2 or more equations, any items that are on either side of the equation, you're going to cancel out, right? So that means that in this case, this chlorine will cancel out that chlorine, this 2ClO will cancel out this 2ClO, and I think that's it.
Cl2.
Oh, Cl2, thank you. Wait a minute, yes, Cl2 will cancel out, right? So basically all the intermediates and catalysts will be canceled out. So what will you be left with? 2NO to form N2 plus O2. No, okay, so now I remember what the issue was. Yes, I don't think, okay, so this will be the answer in terms of the net equation, right? What I'm going to do is I'm going to scratch this question here because not enough information is given to answer this part here. You won't be able to do the rate law based on the mechanism that is provided there. All right, so scratch that one out. Don't need to worry about that one. All right?
Why not? Is it?
Because it's very difficult. It's kind of like a long story, but it's very difficult to treat it the same way as we did in the previous question where we have a reversible reaction taking place. None of these reactions are reversible. And the only thing I could write down, let me scroll back up here. The only thing I can write down in the form of a rate law is for the first step. Let me show you. Which is rate would be equal to, let's say that this is K1, rate to be equal to K1 times concentration of Cl2. The thing is, Cl2 is not a reactant. So therefore, we have to try to find some way of expressing Cl2 in terms of the other products or reactants. And that would work if this was reversible. We could do that, right? Or, well, not even this one. Yeah, this one would have to be reversible, which it is not. So I don't know if there was a typo where that is reversible, but I don't remember where I got this question from. I'll have to go back in my records and see where I got that question from. But don't worry about that. All right. Any questions about this? Any questions? Any questions? Okay, let me clear this. And somebody out there in Zoom was asking about question number 4. Let me scroll back up. Okay, so question number 4 says the reaction of a zero order of a reactant A is zero order. If the initial concentration is 0.545, then, and the half-life is 236 seconds. Answer the following questions, and the first of which is how much time is required to reduce the initial concentration of the reactant by 65.5%. All right, so again, you'd have to figure out or remember what the equation is for a zero order reaction in terms of the concentration relating to the time. And that equation is, I'm going to write it up here, concentration of A is equal to the initial concentration of A minus KT, right? And then the half-life equation for that is concentration, initial concentration of A divided by 2K, right? So those are two equations that you're going to need, okay? Now it says that the, okay, so the question says that the half-life is 236 seconds, and they gave you the initial concentration of the reactant, and the question is asking how much time. So the question is asking for T, right? Now, in order for us to get T, we need the initial concentration of A, and we need a concentration of A at that time. So how shall we do this? Okay, so what I'll do firstly is find out K, right? From this equation here. So based on this equation, K will be equal to the initial concentration of A divided by 2 times T to the half, right? So the initial concentration of A is 0.545 M divided by 2 times the half-life, which is 236 seconds. And according to my calculation, when I did that, I got 1.15 times 10 to the minus 3 M over S, all right? Then I would go to this equation. Now, you have to read the question again carefully. It says how much time is required to reduce the initial concentration of the reactant by 65.5%. So what that means is that the concentration of A at that time would be 1 minus 0.655 times the initial concentration of A. Right? Because what the question is saying is that at this time, 65.5% of A has reacted. So the remaining amount of A would be 100% minus 65.5. So when I did that calculation, let me see what I got here. I got 0.345. So this would be equal to 0.345 times the concentration of A initially, which is 0.545 M. And let me see, what did I get as a result of that? I got 0.188 M. All right? Okay, so we have the concentration of A, we have the initial concentration of A, we have the K value, and we need to find the time. So we have to do some rearrangement of this equation. So basically what this means is that T would be equal to the initial concentration of A minus the concentration of A at that time, divided by the K, which we calculated earlier. So that would be 0.545 M minus 0.188 M divided by the K, which we calculated to be 1.15 times 10 to the minus 3 M over S. And according to my calculations, I got 310 seconds. All right? And that's how we do the A part. Any questions about this? Any questions? Any questions? Any questions out there in Zoom about this one? No? Okay, good. All right. Okay for me to clear this? Can I clear this?
Yeah.
All right. Let me clear. Do this. And let me scroll down. Okay, now the B part says how much reactant remains after 6.78 minutes. Okay, so let me turn this back on. So in this case here, you're going to use the same equation. Now, let me just remind you what the equation is. It's this right here, minus KT, right? So basically, this is, relatively easy because we know what the initial concentration is. We know what T is, we know what K is. All you have to do is plug the numbers and place into these terms here to get what the question is asking for. However, we have to make sure that the units are consistent. Remember, this is in minutes, right? And the K is expressed as what? M per second. So some unit conversion has to take place there where we convert minutes to seconds, right? So the answer is concentration of A is equal to the initial concentration of A, which was 0.545 M minus K, which we calculated to be 1.15 times 10 to the minus 3 M over S times the time, which is 6.78 minutes, but we have to convert that to seconds. So we're going to have 1 minute down here, 60 seconds above, and that's a setup. In terms of units canceling, this will cancel with this will cancel with that. And when I did that calculation, I ended up with the answer being equal to 0.077 M, all right? And that's how that is done. And I just realized another correction I need to make. Well, not correction, but this question you can ignore. It's kind of difficult to calculate how much reactant will remain after 4 half-lives because the half-lives will not remain constant for a zero-order reaction. If this was a first-order reaction, we could do that question, but that's not the case here. So we will ignore C, but that's the answer for B, all right? Any questions about this one? Any questions? Any questions? Any questions out there in Zoom? Okay, so let me clear this. And let me do, scroll down. Okay, now this one is interesting. It says that what time will the reaction be over? So what happens when the reaction is over? Anybody?
Zero.
The concentration of A will be zero, right, exactly. So going back to this equation here. This equation here that we have been working with. Right? The reaction will be over where concentration of A at that time would be zero, and that would be equal to the initial concentration of A minus KT. So what is the time? Time would be equal to concentration of A initial divided by K. And then all we have to do is put the numbers in. Divided by K, which is 1.15, 9 10 to the minus 3, M over S. And according to my calculation, this works out to be equal to 474 seconds. So everything will stop after 474 seconds. Okay. So before your next question, let's take a break. I need a water break. Water. We start back in at 11.
I had a brief question about that last one. Would it actually ever be zero? Like, is like with like typical half-life things, you think about it like approaching zero, if you will, but never like actually getting there? Is that
Okay, so
different?
you're referring to what, the concentration actually ending up being zero?
Yeah, is that like specific to zero order reactions, or is that something that we're
Okay,
to like seven,
good
eight
question.
figures
So-
of zeros, you just call it?
Yeah, for zero order reactions, the concentration will fall to zero.
Will it?
In the
Okay.
case of first order reactions, the concentration will approach zero, but
Yeah.
never get to zero.
Gotcha.
And in the case of second order reactions, I think that can approach zero as well. Hold on 1 minute. Because the thing about second order reaction, the equation for that is, let me see here. Let's play around with that equation. Okay, so for second order reaction, the equation is 1 over the concentration of A is equal to 1 over the concentration of A0 plus KT, right?
Mhm.
So if the thing about this is that, okay, well, let's rearrange this. Let's see what this gives. KT is equal to 1 over the concentration of A minus 1 over the initial concentration of A. Right? So T would be equal to 1 over K times 1 over concentration of A minus 1 over the initial concentration of A. Now, in this case here, if A is equal to 0, this would be infinity.
Yeah.
So infinity minus, well, this is interesting. I never thought of this one before.
Yeah.
This would be infinity. So we're talking about T is equal to 1 over K.
Yeah, you'd have to have an infinite amount of it to
1 over
start with if you
infinity.
wanted to get it to zero, which isn't gonna work.
I mean, this would be infinity
Yeah.
minus 1 over the initial concentration of A.
Uh-huh.
I'm not sure how to interpret that.
Yeah,
Yeah, I'm not sure.
interesting. Yeah, that, I appreciate that. Yeah, I just remember being told that it's always, there's weird behaviors as you approach zero with that and with
Yeah,
one.
that's definitely the first order. It will approach zero. And we're gonna see that again when we get to the chapter dealing with nuclear chemistry.
Okay.
Because first, one of the things you're gonna learn is that all nuclear reactions or all nuclear decay are first order reactions, right? And basically, if you start off with a particular material, which is decaying, the amount would fall off, but it would not, it will approach zero,
Mhm.
but never reaches zero.
Is it more common for the powers to be integers? I know you talked about that we aren't.
Right, okay, actually, it's more common that the powers are not integers.
Okay,
Right?
interesting.
Because most reactions are complex and so on.
Yeah,
And, but for this level, we only stick to integers, 1 and 2 and 0.
is that just for the sake of the algebra, or does it change behaviors otherwise?
Second algebra, because more
Okay.
complex algebra is involved when it comes to more
Yeah.
complex, rate laws.
Okay.
Yeah. Where the integers could be half or even 0.7 or something like
Yeah.
that. The orders are.
Yeah, I'm with you. Thank you.
It's like the hurricane hasn't reached Jamaica yet.
Is it a big one? I haven't been following.
Yeah, so that's a big one, and I remember it might even eclipse the one in 1988, and that was a big one.
Wow.
That was. I'm just looking at let me show you. I'm just looking at they have live cameras at different locations,
Yeah.
so.
It's the hurricane called.
Beryl. They just showed a picture of a normally busy downtown area. Everybody's not there, so.
Hmm.
And that's the Kingston waterfront. Oh, well, let's get back to chemistry. Okay, all right, so we just did question number, what was it, 4?
Yeah.
So, any other problems with this assignment that you guys need help with? Yes, ma'am.
8.
Number 8. Did I number this incorrect? Oh, number 8, okay. Says, consider the following elementary reaction. It gives you that and that. Okay, so this one is relatively simple. It's basically asking for the molecularity. So, firstly, so remember now, the molecularity is basically how many molecules are involved as reactants in that particular step. So the answer for this one would be what? Turn on the pen here.
3?
Nope.
Oh, 2, yeah.
2.
Still 2.
Remember, reactants, not anything else. So for this one, the molecularity is equal to 2. And what about this one? 1. Okay, so in this case, the molecularity is equal to 1. And the rate law expression. So the rate law expression for 1 would be what? Rate is equal to what?
K times the concentration of CO times the concentration of Cl2.
Exactly. And what about the second one?
K times the concentration of HCl was.
Well, actually, that should be iodine. Yeah, so it's HCl. So rate is equal to K times concentration of HCl.
So you don't have to worry about like the order,
What do you mean?
like it's just like CO to the first power. There's no
Right, exactly. If it's just one of them, no, if it was some, right, if it's just one of them, then it's just to the first power.
okay.
But if it was something like, I'm just gonna make up something here. Let's say you had a 2 here, right? Then the rate equation would be K times concentration of CO squared times the concentration of Cl2.
Okay.
You see what I'm saying? So basically, it goes according to the coefficient in the stoichiometry of the equation. And please note that this is only true for elementary steps in a mechanism. This would not be true for the overall reaction. If you remember what I said, I think I said so on the first day. For overall reaction, you cannot tell what the orders are based on the balance equation. But for the elementary steps, like the ones that we have here, you use the coefficients in writing down or establishing the rate law for the elementary steps, not for the overall equation. All right? Okay, okay, so that's number 8.
Wait, why is that? Is that because things cancel, like in the overall, but like why?
Right, exactly.
The elementary step, is that, okay?
Just like we saw in a question earlier,
Yeah,
the overall equation is the result of adding the elementary steps.
yeah.
What you have to understand is that the elementary steps basically are what would, what is more likely to occur in each step. So basically you have molecules colliding. And I think I discussed this in the lecture, in the video. If you think about it, if you use your imagination, you'll realize that it is highly unlikely, well, it is likely that, for example, you can have one atom reacting in a step to form products, right? You can have 2 atoms colliding to form products. It is highly unlikely that 3 atoms simultaneously will collide to form products. So if you look at most of the elementary steps, it's either 1 reactant involved or 2 reactants involved, and that's it, all right? But as you just said, when you add up all the elementary steps, the result should be the balanced equation, all right? And the rate law for that balanced equation, you cannot just tell based on the equation itself. You cannot just use the coefficients of the different substances involved to write down or determine the rate law for the overall reaction. That can only be determined by experiment. Okay. Any other questions on this assignment? Any other questions on this? Let me clear this here. Any other questions on this assignment, or do I need to move on? Equilibrium, one of my favorite topics. How about you guys out there in Zoom? Oh, let me see here. Oh, okay, somebody said number 12, okay. Number 12. Okay, number 12 is the rate law one, okay. If you understood what we did in class, then you should be able to do this, but let me go through this one here. So basically, whenever you're given a question about rate law, the first thing I would do is write down a general rate law. So rate will be equal to the constant, will be equal to K times the concentration of A raised to the, and it doesn't matter what symbols you use. I like to use M and N for some reason. So rate is equal to K times concentration of A raised to the M times concentration of B raised to the N, all right? Where M and N would be the orders of the reaction with respect to A and B. So that's the general rate law. Now, let me see, what did the question ask for? The question asked for, oh, I don't have it here. Okay, it looks like I didn't do this one. All right. So I guess I'm gonna need your guys' help even more in terms of calculation. Okay, so the question is just asking for the rate law. Okay, so let's see here, go back here. So if you remember what we did the last time, what I did was that I plug in the values, I choose a set of data, 2 experimental runs where the concentration of one substance is fixed, right? In this case, concentration of B is fixed for experiment 1 and 2. So I'm going to say for experiment 1, the rate, which is 6.192 M over S, is equal to K times 1.200 M raised to the M times 1.200 M raised to the N. And then I'll do the same thing for experiment 2, 10.800 M over S is equal to K times 1.500 M raised to the M times 1.200 M raised to the N. And then I'll divide the top by the bottom. These units will cancel out, the K's will cancel out, these units will cancel out, and all of this here will cancel out with all of that. So this simplifies to 6.192 over 10.800, and that would be equal to 1.200 divided by 1.500, and all of this would be raised to the M, right? So let me get my cheap calculator and work this out.
We've done this too, I can give you this already.
Oh, okay.
0.5733 repeating equals 0.8 to the X.
Okay, so 0.577.
Sorry, 0.5733
33
equals 0.8 to the X.
0.83.
No, just 0.8 to the X. 80, it's 8 exactly.
Oh, okay. So, and then I'll raise that to the M.
Yeah,
Oh,
sorry, I
okay.
used a different expression.
Okay, no, this one is not directly easy to figure out by inspection. So what you can do is something that you should have learned in math, find a log of both sides. I don't know if you learned that in your algebra courses. And when you do that, you're going to end up with log of 0.5733 will be equal to log of 0.800 raised to the M. And this will be equal to M log 0.800. So therefore, M will be equal to log of 0. Hold on, is this right? 0.5733 divided by log of 0.800. Let's see what this gives.
2.493.
Oh, really?
Yeah.
0.5733. Well, 2.493. Oh, that's unusual. Well, at this level anyway. let me recheck this here, 6.192, 10 by 10.8. Okay. Um, but normally this would be a whole number. Okay. All right, so I'm just gonna go with this here as M, but I can assure you in your upcoming test, exams, whatever, you're gonna get integers. That's basically what is required at this level. Okay, and basically we're gonna do the same thing. Is it okay for me to clear this? Because I need a space. Yeah. All right, so. Okay, so basically we're gonna do the same thing, but this time we're gonna choose the experiments where the concentration of A remains fixed. So that would be experiment 1 and experiment 3, because those two experiments have the concentration of A fixed at 1.200. All right, so again, I'm going to write down the general rate law. And then for experiment 1, the rate is going to be 6.192 M over S equals to K times concentration of A raised to the M. Concentration of B is the same thing raised to the N. And then for experiment 3, that's going to be 17.856 M over S equals to K times 1.200 M raised to the M. And for B, it's going to be 3.100 M raised to the N. And again, we're going to do like we did before. This is going to go, this is going to go, these are going to go. So you're going to end up with 6, let me do it over here. You're going to end up with 6.192 over 17.856. And that will be equal to 1.200 divided by 3.100 raised to the N. And then let's see what this gives. 6.192 divided by 17.856. So this part works out to be equal to 0.3468. And then the other part is 1.2 divided by 0.1. And this is going to be equal to 0.3871. We raised to the N. Let me just check this again. 6.192 divided by 17.856. Okay, so it looks like in this case N is going to be equal to 1. But just to be sure, let me do the same thing as I did before. Log of 0.3468 is going to be equal to N times log of 0.3871. And therefore N would be equal to log of 0.3468 divided by log of 0.3871. So let's see what that gives. 0.3468 log divided by 0.3871 log. So the answer I got for this one is 1.116. I will just round this off to 1. All right. So based on what we just did here, the rate law would be equal to K times the concentration of A raised to the 1 times the concentration of B raised to, what was it, 2.5?
Yeah, you're rounding that for 1.1?
I'd round it off to just one, because like I said, these problems at this level, I'll just give you integers.
Is it okay if I didn't round that in mine?
I'll accept that,
Okay,
right, but for our purposes. And for the other one, I'd round this off to 2.5, because it was 2.49 something, right?
yeah.
So, but I assure you, any future problems that you're gonna get, you're not gonna get integers. I mean, you're not gonna get non-integers, you're gonna get integers. Okay, oh, and let me just say one more thing. So another thing that we covered last time is that you could be asked, even though it's not asked here, you could be asked for the rate constant. Okay, right? And you all remember how we did that, right? All we have to do is rearrange this equation to get K is equal to rate divided by the concentration of A times the concentration of B raised to the 2.5. And then we choose any one of these three sets of data and plug the appropriate numbers in, and that will give you the rate constant. Right? So it's not asked here, but you could be asked that question. And that's how you go about solving that. Okay, any questions about this or any other problems? Other questions? How about you guys all oh, somebody has a question. Oh, okay, somebody's asking for 13. 13. Let's see, 13. Let me clear this first. Okay, 13. Okay, 13, it's the same thing. In fact, it's easier because there's only one reactant. Let's see here. So the general rate law is going to be rate is equal to K times the concentration of ArSO2H, right? So for experiment 1, we're gonna have 4.75 times 10 to the minus 5 m over s equals to K times the concentration of, oh, by the way, this should be an integer here. I'm gonna put m here. So in this case, it's 0.25 m. And then for experiment 2, it's going to be 6.84 times 10 to the minus 5 m over s equals to K times 0.30 raised to the m. You divide the top by the bottom. K's will cancel out. The m units here and here will cancel out. And this will cancel out. So, and the 10 to the minus 5s will cancel out. That makes things simpler. So we're going to end up with 4.75 divided by 6.84, and that would be equal to 0.25 over 0.30, and right there. So let's see what each fraction will give. 4.75 divided by 6.84, and that gives, according to my calculations, 0.694. And then for 0.25, 0.25 divided by 0.3, that would give 0.83. So again, find log of both sides. It should be m here. So the m log of 0.83. So that means that m is equal to log of 0.694 divided by log of 0.83. Now let's hope that this gives an integer. 0.694 log divided by 0.83 log. Look at this. I got 1.96. Now this, I will definitely round off to 2. Right? So the rate law is rate is equal to K times concentration of AR SO2H raised to the second power. That's how we do that. And again, you could be asked to determine K as well. And you know what to do, right? You know what to do, right? So I don't need to go through that. Okay. Any other questions on this assignment? Any other questions? You guys out there in Zoom, any other questions? Okay, going once, going twice. All right, so let me move on now to the next chapter, which deals with equilibrium. And again, I'm going to start you off, but I think I've already published the videos for that one. Let me check and make sure. I told you guys to go ahead and watch it in the meantime. Let's see here. What's happening with this mouse? Let me clear this. Okay, so all right, so let's talk about equilibrium. And we referred to it earlier when we were discussing a particular question from the previous assignment. So we're going to get into more detail about this. So basically, first thing I'm going to talk about is what we call reversible reactions, right? And we saw an example of that in the assignment that we gave before, right? A reversible reaction is basically a reaction that can go both directions. In other words, you start off with a particular reactant or reactants, the reaction takes place, it forms the products, and then the products themselves will react to form the original reactants, right? So we call those reactions reversible reactions. And pretty much all reactions are reversible. It depends on the conditions that are applied at that time. So for example, just to give you a simple example, it is possible to have this reaction. It's a simple example. The reaction of water to form hydrogen and oxygen, right? And to balance that, we're going to need this and this here, right? But it is also possible for hydrogen and oxygen to form water, right? So this reaction is reversible and it's all a matter of conditions. Now in this case, in order to perform this reaction, we'd have to pass an electric current through this. So we call this electrolysis. In this case, all we have to do is apply a flame to a mixture of hydrogen and oxygen, and you form water, right? So I can't think of any exceptions. So I would just go to the limit and say that pretty much all reactions are reversible. Now, when it comes to an equilibrium system, that's a special situation of a reversible reaction, right? We say that the system reaches equilibrium, a state of dynamic equilibrium, when the rate of the reverse reaction and the rate of the forward reactions are equal to each other, all right? So both reactions are reversible and they're proceeding at equal rates. I'm sorry, let me get rid of this here. Okay, so this is just a graph showing you what we're talking about here. The y-axis represents the reaction rate and the x-axis represents times, right? So what happens if we start off with a certain amount of reactant, then basically what will happen is that the concentration of the reactant will decrease as the reaction progresses, And the consequence of that is that the rate of the reaction will decrease as well, right? At the same time, you have the product being formed, right? And as the reaction proceeds, you have more and more products, which means that the rate of formation of products will increase, right? So you have the rate of the reactants decreasing, the rate of the formation of products increasing, until you get to a state of dynamic equilibrium, where the rate of both the forward and reverse reaction will be the same, all right? And that pretty much continues on to infinity as long as the conditions are remaining the same, all right? So that's basically what we mean by an equilibrium system in the context of a reversible reaction, all right? Okay, so to give you a pictorial representation of the fact that we can actually know that this is happening in certain situations. So here we have a situation where we have a saturated solution of sodium chloride, right? So what that means, and I think you should know about this from before, you add a lot of sodium chloride to a relatively small amount of water until the water cannot dissolve the sodium chloride. So basically, you're going to have your saturated sodium chloride solution here, and you're going to have some sodium chloride solid here. So basically, we can represent the state of affairs in terms of a reversible process. It's not a chemical reaction per se, but the same principles apply, where you have an equilibrium between sodium chloride solid and sodium chloride aqueous, right? That's what happens when the sodium chloride solution is saturated. You have the back and forth, right? Now, what this person, whoever this person is, decided to do is to add some sodium chloride, but the sodium ion is radioactive, all right? Right, so you're adding sodium chloride containing radioactive sodium ions present, right? So that can be detected. We have instruments that we can use. There's one that's called a Geiger counter where you can use it to detect the radioactive form of a particular element. So when this person added sodium chloride to the radioactive sodium chloride to the aqueous solution, then what happens eventually is that not only do you have solid sodium chloride that contains radioactive sodium, but eventually the solution itself will contain the radioactive sodium. So what does that tell us? It tells us that there's a back and forth taking place between the solid sodium chloride, right, and the sodium chloride in the aqueous solution, right? Because in this case, we added solid sodium chloride with radioactive sodium in it, and eventually some of it ended up in the solution. So we know that there is a reversible reaction taking place, and then what will happen eventually is that the amount of radioactive sodium chloride present in both the aqueous solution and in a solid state remains the same. So that's what this pictorial representation is all about, right? The sodium chloride dissolves and recrystallizes continuously. That is represented by the equation I had here. And after time, when you're adding the radioactive sodium, then some of it will get into the aqueous solution as well as in a solid state. All right, so that basically illustrates the principles involved in a system that is under a state of dynamic equilibrium. Okay, now we're going to look at another example, which is actually more quantitative. Let me erase this here or clear this. So in the next example here, okay, what's going on? Okay. So what we're looking at now are some graphs that represent some changes in concentration for a system as it approaches equilibrium. Now, the equation is not given, so let me see if I can squeeze it down here at the bottom. The equation I'm about to write here is the equation for the reaction between, you do it here, hydrogen iodide to form H2 and I2. And to balance this, we need a 2 here, right? So that's the equilibrium system that is we're looking at here in terms of looking at the changes in concentration. All right, so let's look at each of these graphs, starting with experiment 1. So in experiment 1, this experimenter decided to start off with a 1 molar concentration of HI, right? And they allowed the reaction to take place. So you're starting with only HI and no hydrogen and no iodine. So of course, what we would expect, we would expect that the concentration of hydrogen iodide would fall off, right? And that continues until it flattens out right here. And at the same time, because some hydrogen iodide has reacted, then the H2 and I2 will be produced. So you see that it increases, the concentration for both of them increases from 0 to about 0.107, right? And you'll notice that the concentration of H2 and I2 are the same because it's a 1-to-1 mole ratio between these two, right? And you'll notice that that flattens out as well, right? So basically we're talking about an equilibrium state from that point forward, right? Because the concentrations of all the components, the hydrogen iodide, the hydrogen and iodine remains constant, right? So that's what happens in the case of experiment 1. Let's look at what happens in the case of experiment 2. In the case of experiment 2, we started off with a certain amount, 1.0 m of both hydrogen and iodine, and no hydrogen iodide. And what happens? The concentration of hydrogen and iodine falls off, as you would expect, because you only have H2 and I2, they will react to form HI. So what happens as far as the HI is concerned is that its concentration increases from, of course, nothing to a certain value. And then at equilibrium again, the concentrations of everything remains constant, all right? So in experiment 1, we started off with only hydrogen iodide and nothing else. In the case of experiment 2, we started off with H2 and I2 and no hydrogen iodide. And now in experiment 3, we're starting off with 1 molar of both HI and H2 and I2. And what we notice happening here is that the concentration of HI would increase and then it flattens out. And the concentration of H2 increases, or I should say decreases, and it flattens out, right? And again, where it flattens out, that represents the equilibrium state, all right? So that's basically what happens in each of these cases. So what we're going to look at next, and let me just skip all the boxes here because I described these already. So what we're going to do now is try to make sense of this data, right? See if we can find some, order, pattern, whatever, all right? So these are the data that we got, which resulted in the graphs that we just looked at, right? So as we said before, in experiment 1, we started off with only HI, no hydrogen, no iodine, and these are the resulting equilibrium concentrations. And we did the same thing for experiment 2 and experiment 3. These are the data, again, which produces the graphs that we saw. So what this experimenter did was to try to make sense of the data. So what they did was divide the product of the concentration of the products by the concentration of the reactant and see what the result is. And this is the result they got, 0.0146, 0.0288, and 0.434. Doesn't make too much sense. There's no rhyme or reason in terms of the result of that calculation. So what this experimenter decided to do was to take into account that you have a 2 here by multiplying the concentration of HI by 2, and we get these numbers. Again, no pattern emerging as a result. Then what this person decided to do was, instead of multiplying the HI concentration by 2, they decided to raise the concentration of HI to the second power. And what do we notice here? Pretty consistent, right? Not exactly, of course, because, of course, the nature of experiments is that there's some fluctuations, but they're very close, right? 0.0185, 0.0183, and 0.0184, right? And this is what you'll find for pretty much all equilibrium systems, right? What you'll find is that if you take the product of the concentration of the products raised to their coefficient power and divide that by the concentration of the products of the reactants, and again raising that to their respective coefficient power, then you're going to get a constant value for that ratio. So generally speaking, and this is just a general hypothetical case, if you have this system in equilibrium, right, where the upper case represents the formulas of the substances and the lower cases represent the coefficients, then we can write down a general equilibrium expression where Kc, which is a constant, is equal to the concentration of G raised to the G power times the concentration of H raised to the H power, all divided by the concentration of A raised to the A power times the concentration of B raised to the B power, right? And we find that experimentally, that ratio is going to give a constant. Please note that each of these concentration terms must be raised to the power of its coefficient, which underscores the importance of having a balanced equation to begin with, right? Because if the equation is not balanced, then the coefficients will be wrong. And if the coefficients are wrong, then the calculated Kc value will be wrong as well, right? So it's important that you start off with a balanced equation and then you apply the expression right here. Another thing I want to make mention of is that for the calculation of the Kc constant, the convention is that we put the product terms as the numerator and the reactant terms as denominators, all right? So make sure it's products over reactants when calculating the Kc expression. Okay, so the Kc expression, or I should say the Kc constant, we call that the equilibrium constant. Let me write this down here. So Kc, we call that the equilibrium constant, all right? And as I'm going to indicate later on, I can say so now, that constant will be a constant that will be constant when the temperature is constant, right? So if the temperature is constant, the Kc doesn't change, right? And later on, we're going to learn how temperature affects Kc, but that's for later on in this chapter, right? But as long as the temperature is constant, the Kc remains fixed. And that's why you'll notice in certain questions that we're going to look at, whenever they quote a Kc value, they always quote along with it the corresponding temperature, right? Because temperature does affect the value of Kc. All right, so let's talk about the equilibrium constant. Some facts about the equilibrium constant. The constant is constant regardless of how much reactants or products you start off with initially. And that is important when it comes to doing certain calculations you're going to see later on. I mentioned this before, the Kc is called the equilibrium constant, and more specifically, it's called the concentration equilibrium constant, because what you're going to learn is that there are different types of equilibrium constant. This particular equilibrium constant is based on concentration values, but there are other equilibrium constants we're going to learn about later. For example, we're going to learn about Kp, which is the equilibrium constant, which is based on pressure values, for example. And there's some others as well. I mentioned this also before, so this is just for emphasis or re-emphasis. When setting up the Kc expression, it's always products over reactants. So the concentration of the products being the numerator and the concentration of the reactants will be the denominator. Another important factor or fact you need to keep in mind is that the exponents of the concentrations will be the same as the coefficients in the balanced equation. So therefore, as I said before, make sure that the equation is balanced, all right? A wrong equation or an unbalanced equation can potentially result in the incorrect Kc expression and therefore the incorrect calculated Kc value, all right? Okay, what time is it? All right, so let's look at this example. It says, if the equilibrium concentration of COCl2 and Cl2 are the same at 395 degrees Celsius, find the equilibrium concentration of CO in the reaction, right? So the equilibrium concentration they're asking for of CO. So the first thing I would do is write down an expression for Kc based on what we have learned. So Kc will be equal to the concentration of the product, which is the concentration of COCl2, divided by the concentration of the reactant, excuse me, which is CO times concentration of Cl2, right? And that would be equal to Kc, which is equal to 1.2 times 10 to the 3. So the question says that the concentration at equilibrium of both COCl2 and Cl2 are the same. So what does that mean? This will cancel out with that, right? If they're the same, right? So this simplifies to 1 over the concentration of CO, right? So therefore, the concentration of CO be equal to 1 over 1.2 times 10 to the 3, which would be equal to 8.3 times 10 to the minus 4. And that's it. And by the way, and I probably should have mentioned this before, when it comes to calculating any equilibrium constant, the convention nowadays is that we don't include the units. All right? That was different from back in the Stone Age when I was a student. Because when I was a student, we had to, as students, figure out the units for Kc and the other equilibrium constants you're going to learn later on. But somewhere between my college years and when I went to grad school, they changed the rules. So now you guys don't have to worry about the units for Kc or for any other equilibrium constants, right? So that's why here you don't say the units for Kc, right? You still have to include the units for concentration like this, right? But for the actual Kc values or Kp or whatever K values you're going to use later on, no units required, all right? So just something for you to be aware of. Okay, any questions so far? Any questions? Yes, ma'am.
The COCl2 and the CO2 cancel out?
Because they're equal. It says if the equilibrium concentration of CO2 are the same, right? So that's why we can cancel them out, all right? Okay, any other questions? Any other questions? All right, so let's talk about modifications. Oh, yes, sir.
Oh, why aren't the concentrations of CO and Cl2 gonna be the same?
Well, that's what the question says. The question just stipulated that they'll be the same. They don't have to be the same.
The two reactants on that equation, why aren't they gonna be the same? Don't they have the same amount of moles?
Well, in the balance equation, yes, but you could, set up the experiment where the concentration of, like you're going to mix them together, right? And you could set it up so that the concentration of CO2 is something.
Okay, so you could purposely start them so they're different. But
Exactly.
if it started out with the COCl2, it would likely be the same.
Exactly.
Okay, got it.
Right, exactly. Okay, so any other questions? Any other questions? Okay, so let's talk about some modifications to the chemical equation and how that can affect the, clear this, how that can affect the Kc expression and Kc values. Okay, so let's consider this particular equation, right? This reaction. And it was determined that the Kc value is equal to that, right? So of course, by now we know how to set up the equation based on the balance equation. Or set up the expression based on the balance equation, right? So this is it right here. Kc is equal to the concentration of NO2 squared divided by the concentration of NO squared times the concentration of O2. And it was determined that at 298 Kelvin, the Kc value is 4.67 times 10 to the 30. Now, that's for this equation. Now, let's look at this equation, right? Now, first thing I'm going to ask you is this. What's the difference between this equation and the first one I gave you before? What's the difference?
It's the reverse.
Exactly, we just switched it, right? Right, the products of the first equation will be the reactants of the second equation and vice versa, right? So how does that affect the Kc for the new equation that we have here? So what we're going to do is call the new Kc value K prime C to distinguish it from the original Kc value that we have, right? So if I were to write down the K for Kc for this new equation here, it would be this right here. The concentration of NO squared times the concentration of O2 divided by the concentration of NO2 squared. And this equation here would be 1 over this expression right here. And this expression here is equal to Kc. So therefore, Kc prime would be equal to 1 over the original Kc. And the original Kc value is 4.67 times 10 to the 30. So we just do 1 over that value, and that gives you the Kc for the reverse equation. All right? So basically what you'll find that this is true pretty much in all situations of this type. The Kc for the forward reaction will be equal to 1 over Kc for the reverse reaction. And that is true pretty much all the time. So if you know the KC for the forward reaction, all you have to do is 1 divided by the KC for that reaction for the reverse reaction. All right? Okay, any questions about this? Any questions?
Yes,
Yes,
sorry, I think I missed the point. What is the purpose of having the K product? What does that help with?
To make a distinction between the KC for the forward reaction, which is KC, in colored red, and the KC prime for the reverse reaction.
So you can just interchange them.
Exactly, right, exactly. And you're going to see the importance of this later on when we can come to some more complex problems. Okay, any other questions concerning what we just covered here? Any other questions? Okay, let's take another break before we move on to some other modifications. Let me see what's happening at home. Oh, nothing yet. Any one of you here are products of the Marion County School, public school system? You? What do you call it? The Florida Assessment of Student Thinking Test. What kind of test is it?
The what?
Florida Assessment of Student Thinking Test? Oh, you don't know? Okay.
It's a new test. So you know the FSA, right?
Uh-huh.
It's like, so they think that the FSA was bad, so they tried to replace the FSA with FAST. So instead of, it's, FAST is more to see like your progress,
Uh-huh.
basically, while like throughout the year, while the FSA is like, just at the end, see what you did. So like, it's graded, but like, it's not to see.
Is it a pass fail or is there like a letter grade or anything?
No, it's still like that to say it's like 1, 2, 3, 4, 5. But like, it's more to see your progress and not to, like, throughout the year and not at how the FSA was, where you see what you learned all throughout the year in one test,
Oh,
So it's multiple tests instead of one.
Yeah.
And it's throughout the year to see progress instead of just like, if you got the knowledge.
Yeah, basically.
okay.
They keep on changing the test.
Yeah, because I remember when I first moved to Florida, there was a big uproar about the previous one that you were.
It was FCAT, then it was FSA.
Right, FCAT, I remember FCAT, that's the one that everybody was, making a big issue about. So I didn't hear about this one before, I was just scrolling through and I came across that one.
They'll probably change it in a couple years.
I saw a news item which says that Marion County Schools perform like one of the worst in the state. And then I saw this article which says that it has improved, so I don't know what that means. Right? Says school officials say students showed notable improvements during this year's Florida Assessment of Student Thinking test. I need to save this to read this later on. Oh, so it's the second year of this thing.
You still have family back in Jamaica?
Yeah.
Are they doing all right?
As far as I know. They arrested a Marion County teacher for murder. Yeah, but they know teachers were.
People actually are notorious though, because they just,
What's that?
they're notorious. They just arrested a couple teachers for like sexual assault and all that stuff. I know the school that I came from, there was like a volleyball coach and a Spanish teacher that used to have kids over at his house and partying.
Some people are just stupid, man. This area here, usually during the day, busy.
Oh, God.
Okay, let's restart. All right, so we talked about modification of the equilibrium constant as a result of reversing the equation. Come on, where are you? Okay, so. Okay, so that's what we just did. Okay, so let's look at what happens if, again, we're starting from the original equation, for which the Kc is equal to that. And now we're going to look at this equation right here. So my question to you is, again, comparing the two, what's the difference?
Dividing the coefficients by 2.
Right. You divide the coefficients, all the coefficients in the first equation to get the equation, to get the second equation, right? So now we're gonna look at how does that affect the Kc value? Oh, that's one difference, but there's another difference.
And it's the reverse reaction.
Exactly, the equation is flipped, right? So we have done two things in order to get from the initial equation to the second equation. We divide all the coefficients by 2 and we flip the equation. So how does that affect the new Kc value for this equation here? We're going to call it Kc double prime, right? So basically, based on this equation here, Kc double prime is going to be equal to the concentration of NO times the concentration of O2 raised to the half power divided by the concentration of NO2. And if you compare this expression to this expression, you'll see that this expression will be equal to 1 over all of this here. So in other words, Kc double prime will be equal to 1 over Kc raised to the half. Right? So all we have to do now to find the new Kc value, the Kc double prime, is to put the Kc value of the original equation here and then do the math. And you're going to end up with the new Kc equation or Kc value, Kc double prime, would be equal to 1.467 times 10 to the minus 7. Yes, sir.
Is the Kc double prime, is that specific to switching the sides and dividing by 2?
Exactly, exactly.
It seems like a kind of niche thing to do. Is that a common situation?
It's common for solving certain problems,
Okay,
which we're going to see later on.
okay.
All right. In fact, I think the next, well, before I move on to that slide. So I want to make sure everyone understands what's happening here. Any questions about this? Any questions? Any questions? All right. So just some general comments here concerning modifications of the chemical equation and how it affects the Kc values. For the reverse reaction, the K for the reciprocal of K for the, I'm sorry, for the reverse reaction, K is the reciprocal of K for the forward reaction. That is, what we talked about earlier. When the equation is divided by 2, right, to get the new equation, then the K for the new reaction is the square root of the K of the original reaction, right? So basically, we saw that again earlier, divide by 2, that means that the Kc value will be square rooted. In fact, here's a general rule right here. When the coefficients of an equation are multiplied by a common factor n to produce a new equation, we raise the original Kc value to the power of n to obtain a new equilibrium constant, right? So if you have an equation and you know the Kc value for that equation, and then you multiply that equation by, let's say, 2, then the new Kc value will be squared. right? If you multiply by 3, then the new KC value will be cubed and so on. If you multiply right through by half, then the new KC value will be square rooted and so on and so forth, all right? And again, I said this, I think, at least 2 times already, and I'm gonna say this again. Make sure you start off with a balanced equation, right? The equation that you start off with, whenever you're working with any KC expression, must be balanced, all right? Right? Because obviously, if the equation is not balanced, then the KC expression would be incorrect, more than likely, and therefore the resulting KC value would also be incorrect. Okay, let's look at this example right here. It says that the equilibrium constant for the reaction, and it gives you the equation, at 718 Kelvin is 7.07. So the question is asking, what is the value of KC for this equation? So how would you tackle this? Turn on my pen. All right, so any ideas? I'm gonna call this KC prime. What would that be equal to? Exactly, 1 over the original KC, which is 1 over 7.1, I'm sorry, 7.07. Which is equal to what?
0.141.
0.141. Okay, and then what about this one? I'm gonna call this KC double prime. That would be equal to what? Comparing this equation to this equation, what do you notice? Exactly, so KC double prime will be equal to KC squared, which will be equal to 7.07 squared, should be equal to 49 point, call it 50.0. All right, that's it. Okay, any question? Oh, yes, sir.
For A, you did 1 over the original KC because it
It's
was
flipped.
first.
Right, the equation is flipped, so therefore, when you flip it, the KC would have to be inverted, 1 over the original KC, right? Okay, any other questions? How about you guys out there in Zoom? Any other questions? Okay, I'll take that to mean you have no problem with this, so let me clear this. And let me do this. And move on to the next slide. Okay, now let's look at this equation right here. Slightly bit more complicated, right? And let's say that you're given these 2 equations right here, right? So for this equation, the KC value is given. For this equation, you have another KC value, right? And the question is asking for you to determine the KC value for this equation based on these 2, right? Now, if you look at these 2 equations here, you'll notice, especially when compared to this equation, you'll notice that you can add these 2 equations here to get this equation. So let me turn on the pen here. So basically, if you add these 2 equations, and again, this is something you should remember from your previous chemistry experience. When you add 2 equations, you cancel those items that are identical on both sides, which would mean that the NO here and NO here would be canceling out, right? So what you'll be left with would be N2O, which is this, plus 1.5 oxygens, which is the same thing as 3/2, to give 2 NO2, which is this right here. So the question now becomes, if you add these 2 equations to get this equation, how would you use that idea to get the KC value here for the net equation based on the KC value for the individual equations provided? And the answer is, basically what you have to do is add, when you add 2 equations together, you have to multiply the given values of KC of the equation that you're adding together, right? And that will give you the KC of the net equation. Now, I can show you why that is so. So what I'm gonna do is, I don't think, let me see here. Okay, I have to show you on a separate application. So let me, what shall I use? What shall I use? Actually? Okay. I'm gonna use Word. Okay, so uh, I'm gonna do some copy and paste here. I want the local copy. Okay, this is messed up. Anyway, I'll work with this. Okay, let me leave that as it is, right? Okay, so what I'm gonna show you is why is it that when you add two equations together, you have to multiply their respective KC values, all right? So let me, this, okay. So basically, you know what, I don't have to use that. Let me use the word. Okay, so, okay, good. All right, so I'm gonna put the arrows here to indicate the reversibility of these reactions, right? So, as I said before, when you add these two equations together, the NOs will cancel out, and you'll be left with N2O plus 3/2O2 to give 2NO2, right? So the question is, what's the KC value for this reaction? That's KC1 for the purposes of this. Now, let's write down what KC3 is equal to based on this. That would be equal to concentration of NO squared, NO2 squared, divided by the concentration of NO squared times the concentration of O2, right? And then KC2 is equal to the concentration of NO squared divided by the concentration of N2O times the concentration of O2 raised to the 3/2 power. So that's KC3, that's KC2, right? So what I'm gonna do, yes, sir.
Isn't the KC, isn't there gonna be a 1/2 exponent for that 1/2 oxygen? In that equation?
You mean here? This is half and this is one.
Yeah,
So when you add them up, you're gonna get 1.5, which is 3/2.
I guess I'm confused, which one, or what are we labeling, which one is which? Which one is K2 and which one is K3 of those equations?
This is KC3 here.
Okay, and then all those
This is
cases.
KC2.
Gotcha, thank
And
you.
I'm gonna show you how we get KC1, all right? Okay, so this is KC3, this is KC2. So what I'm gonna do is multiply KC3 by KC2. In fact, let me just do that right here. So I'm gonna say KC three times KC two would be equal to concentration of NO squared divided by concentration of NO N2O times the concentration of O. Okay, I'm doing something. What am I doing wrong? KC. Hold on. Okay, I think I mixed up something here.
I think the KC2 oxygen should be 1/2 exponent rather
My
than 3
bad.
half.
Yeah, my bad. Thank you for pointing that out. All right. So the KC2 I should be using should be this right here, right?
Yeah.
Which would be concentration of NO squared divided by concentration of N2O times half, or concentration of O2 to the half. Okay. Yeah, that's my fault. Okay. So let me erase this here. So when I'm multiplying KC3 by KC2, I'm multiplying this here by this. I'm going to put concentration of NO squared divided by concentration of N2O times the concentration of O2, right? Okay, so
Oh, yeah, sorry.
to the half,
No, yes, yeah.
to the half. Right. So let me erase this here just for the sake of avoiding any confusion. So this is KC3 times KC2, which is this multiplied by this. And what you'll find is that this will cancel with that, all right? And you'll be left with concentration of NO2 squared divided by the concentration of N2O times the concentration of O2 raised to the 3/2, right? And if you look at this code closely, excuse me, you'll see that this is the same thing as KC1, KC4, this equation right here. So basically multiplying KC3 by KC2 will give KC1, right? And this is true whenever you're adding equations, right? If you add them together, the net KC value would be the product of the KC values of the individual equations you're adding, right? So that's basically how that works, all right? Okay, any questions about this? Any questions? Any questions? Okay, so let me go back to the PowerPoint. All right, so we're finished with this. Basically, the net result is that whenever you're adding equations, to get the corresponding net KC value, you multiply the individual KC values for the equations that you're adding together. Okay, so now we're going to get into a different types of equilibrium constant where we're dealing with reactions involving gases. So if we have a totally gaseous system at equilibrium, then we have a corresponding equilibrium constant called Kp, right? So Kc, if you remember, expresses the equilibrium constant in terms of concentration. Kp does the same thing, but this time it's only for gases. So as you can see here, Kp is equal to, and again, this is based on the same hypothetical example. Let me remind you, the same hypothetical example that I gave you earlier, right? Where shall I put it? Let me squeeze it up here. We're talking about AA plus BB to give GG plus HH, right? So we're assuming that these are all gases, right? Totally gaseous system, all right? So in that particular instant, this is the Kp expression. Each of these terms represent the pressures of each gas. We call them partial pressures, right? Each of these terms represent the partial pressures of each gas in a system, right? And again, just as in the case of concentration, you raise the partial pressures to their respective coefficients in the balance equation, all right? Now there's a relationship between Kp and Kc, And that relationship is given by, oops, okay, what am I doing here? Okay, given by this equation, right here. Okay? The equation is right here. And that is Kp is equal to Kc times R times T raised to the delta N. Now, the R that you're going to use here in this equation is the R that you would have been accustomed to from your Chem 1. R is equal to 0.0826 liters atmospheres over mole Kelvin. And the T is the temperature in Kelvin. And the delta N is a special number. It is a difference in the sum of the coefficients of the reactants minus the sum of the coefficients of the products. All right? So basically, once you determine all those numbers, then you can go from Kc to Kp and vice versa. All right? So that's a relationship between Kc and Kp. Okay, so just to give you an example. Okay, get rid of this here. Okay, so in this example, they gave you an equation, right? And they gave you the corresponding Kp value, right? And the question says, what is the value of Kc for this reaction? So as we said before, Kp is equal to Kp is equal to Kc times RT delta N, right? So what the question is asking for is Kc. So Kc would be equal to Kp times RT to the minus delta N, all right? So we put the numbers in. Kp is 0.660 times R, which is 0.0821 times the temperature. What's the temperature? 319 Kelvin times delta N. So what is delta N? Right, it's here. Delta N would be equal to the sum of the coefficients of the product, which is 2, minus the sum of the coefficient of the reactant, which is 1. So we're going to put 1 right here for delta N, right? And that's it. So let's see what that gives. 0.0821 times 319 multiplied by 0.660. So according to my calculation, the answer is 17.3. Right? And that would be the answer for the A part. All right? Any questions about that? Any questions? Okay, the B part says, the B part says, what is the value of Kp for the reaction? And look at the reaction. When you compare the equation in B to the original equation, what do you notice? It's flipped. So how do you think we calculate the Kp for B? Let me clear this here.
1 over Kc,
No, 1 over Kp.
Kp, yeah.
Exactly. So in the case of B, Kp, I'm going to call it Kp prime. In the case of B, that will be equal to 1 over the original Kp, right? Which is 1 over 0.660. So 0.660 and 1 over that. According to my calculation, that works out to be 1.52. All right? Any questions?
Would that have worked if you just used your Kc prime value and then put it into the original Kp equation?
Yeah.
That would
Yeah.
also work?
Yeah. That's a longer route though, but yeah,
Gotcha.
it would work, yeah. Okay, and then we get to C. In the case of C, it says, if the equilibrium partial pressure of NO2 is 0.332 atmospheres, what is the equilibrium partial pressure of N2O4? So basically, this is what we would use. Kp, based on this equation right here, Kp would be equal to the partial pressure of NO2 squared divided by the partial pressure of N2O4. Now, what the question is asking for, what the question is asking for is the partial pressure of N2O4, right? So I would rearrange this to get partial pressure of N2O4 would be equal to the partial pressure of NO2 squared divided by Kp. Now, the partial pressure of NO2 is given as 0.332 atmospheres divided by the Kp, which is 0.66. Oh, by the way, this should be squared. All right, 0.660. So let's see what that gives. 0.332 divided by 0.660. And according to my calculations, this works out to be equal to 0.503 atmospheres. That's basically how that is done. All right? Any questions about this example? Okay, now I think you've heard enough of me. So what I'm going to do is get you started on assignment number 3. And for those of you out there in Zoom, I'm going to publish it shortly. And for now, I want you to focus on question numbers 1, 2, 3, and that's it. Questions 1 through 3. And let me publish that assignment for you guys out there in Zoom. Okay, so let me go here. No, number 3. Okay, so for you guys out there in Zoom, assignment number 3 is now available, so you can get started on it. As I said before, we're focusing on questions 1 through 3.
As in 1A is like whether all gases, does that mean we're just doing the Kp value?
Well, the question says, calculate both Kc and Kp. So you're going to do Kc and Kp, which you can do for all of them because they're all gases. So you're going to write down the equilibrium. Let me show you for the first one. You're going to write down the equilibrium expression for come on. Okay, so for the first one, you're going to write down the Kc expression, which would be Kc is equal to the concentration of Hi squared divided by the concentration of H2 times the concentration of I2. And then for Kp, that would be equal to the partial pressure of Hi squared divided by the partial pressure of H2 times the partial pressure of I2. And that's it.
And that Kc value works, that you can use that even though they're all gases?
What do you mean?
I don't know, I kind of assumed it was, since there was a special one for pressures and gases, that the one that was just the equilibrium constant that wasn't for it was for, say, liquids or something. that wasn't
Okay, I
gases.
get what you're saying. So yeah, you can use KC for pretty much any system. It doesn't matter if it's totally gaseous.
Then
But
what,
But KP is specifically for gases.
so do they differ when they're in the same, when they're both for gases? Why do you need a second one for
They
gases?
differ, excepting under one particular circumstance. And that is if the reaction is equimolar, which means that the number of moles of gases on both sides would be the same. So in the case of this particular reaction, you'll notice, and I probably should have made this point earlier, you'll notice that you have 2 moles of gases on this side.
Yeah.
And 2 moles of gases on this side. In that particular circumstance, Kc is going to be equal to Kp. But under other circumstances, that would not be the case.
Gotcha. I guess I'm struggling to understand what extra information you gain from KP. Why is there a specialized version for the gas?
Well, because gases behave much differently compared to solids and liquids and solutions. And you can have a totally gaseous system, and therefore it's more convenient to measure the pressure as opposed to concentrations.
Gotcha.
So that's
But
a
yet
reason.
despite those differences, you can still have a KC value that generally.
Exactly, you're still right, because, and actually we can, because remember I gave you this equation, Kp is equal to Kc
Yeah,
times R. We can actually derive this. I didn't go through it, but I can show you how to get from, how you get this expression, this relationship between Kc and Kp.
so why, sorry, I don't mean to keep on.
Yeah, no,
So
go for it.
why would you use KP then? Is it more accurate? Like if you're
Like I
comparing
said,
two gases, why wouldn't you just use KC?
Well, like I said, it's more convenient, because when it comes to gases, it's more convenient to measure pressure as opposed to concentration. So that's why we have a Kp.
Gotcha, so you have a specialized value for
Right.
KP for the ease of measurement for
Exactly,
practicality.
but
Okay,
you
thank
still
very
can
much.
use, you still
KC
can.
still works, but it isn't practical because you're not gonna be able to measure the concentration and something like that.
Right, exactly,
Okay.
but you can still determine the concentration or
That
Kc,
makes a lot of sense.
Right,
Thank you very
exactly.
much.
exactly.
What all do you want us to say for number two when you say, describe how it's related to KC? Want us to show our, like a calculation or just?
Yeah, you have to calculate it. So it's kind of similar to the problems that we're looking at earlier.
Okay,
So like for the first one, here. So like in the case of, this one right here.
Yeah.
This is the reverse of this. That means that the KC value for this would be one over the KC of.
Yeah. Gotcha.
Just for the calculation and that's.
And for the other ones, do you want us to all relate it back to the first equation or do you want us to say,
You don't
oh,
have to, you could relate it to,
any of them? So you could say
Yeah.
this one is this
you get the
word.
same result.
Okay,
anyway.
okay, gotcha, thanks.
Sure, I do the questions for number three. Could you go?
For number three. Okay, for some reason this mouse is, okay, number three. Okay, so this one is asking for you to express KC in terms of KP for each of these reactions. So it's kind of similar, hold on, somebody has a question. Oh, so in answer to your question, Julio, basically I'm just giving you some time to work the problems I mentioned in assignment 3, questions 1 through 3. So if you have any questions while working them, now's the time. So I'm gonna answer a question now that is being asked here concerning question number 3. So if you recall, the relationship between KC and KP is KP is equal to KC times RT raised to the delta N. What the question is asking for is KC in terms of KP. So what I would do is rearrange the equation to get KC is equal to KP times RT to the minus delta N, right? Delta N. So in the case of this equation here, the answer would be KC is equal to KP times RT raised to the minus, and delta N would be, in this case, delta N would be 2 minus 3 plus 1, which is 4. So this would be minus 2. So this would work out to be KP RT squared. And that's pretty much all you're going to do for all of them. The key thing that you need to figure out in these questions is what delta N is, right? And delta N is the sum of the coefficients of the products minus sum of the coefficient of the reactants, right?
Delta N is, what again?
It's the sum of the coefficients of the products minus the sum of the coefficients of the reactants.
It's just to work through 3, right?
Yeah, you're finished. That's pretty much it. In fact, you can leave now if you want to. But then before you guys leave, so let me just say, I probably should post this in the announcements. So assignment 2, make sure you finish it up and make sure it's clean and nice and so on. And I've opened up a Dropbox for assignment 2. Okay, so open the Dropbox assignment 2. And that is due tomorrow at midnight. And that's one. There's something else I need to say to you guys. As far as this current chapter, make sure you watch the videos for equilibrium. Now, I gave a head start. The videos are located, of course, under the modules. So far, I've discussed everything up to here. So you need to watch the rest of the videos as well. There are some examples that I've worked out as well. And if you have any questions concerning any of these, feel free to contact me. And I'll be more than willing to help you out. All right? I think that's all the announcements I have for now. Oh, and another thing, I've figured out how to post the YouTube videos for these classes. So I'm going to post it in the module section later on, so that if you need to go back and remind yourself of something, whatever, you can do so. All right, so that's it. See you guys on Monday. Well, I'll be seeing some of you in the lab later on. So.
Thanks so much.
Yes, sir. um,